In this video, I will take you through the physical interpretation of a derivative and in fact the usability also. We do look at the derivative in terms of speed, okay. So there is a certain distance that you travel in certain time, right? So say I'm moving from time t to t plus delta t, that is the change in time. So in time delta t or change in t, how much have I traveled? If my traveling function looks like this, the distance function looks like this, I'm moving from p to q, okay, I'm moving from p to q. What is the change in the distance? The change in the distance is the following. The change in the distance is the following, right? Now that would, so change in f upon change in t, change in f upon change in t, or let me just put it as change in d upon change in t, okay, d by t would give me my speed. That would be the average speed, right, from say 8 to 10 minutes. So essentially 2 minutes, the difference is 2 minutes. I travel from 8 to 10 kilometers, okay. So that means 2 kilometers in 2 minutes. That means on an average I am traveling 1 kilometer in 1 minute, right? So that is the average speed. So essentially, when we're finding derivative, what are we looking at? We are looking at change in f upon change in x, which is my difference quotient, right? Now this essentially is an average change, okay. The moment I interpret my change in f as actually change in distance, right, and change in x, let x be t, time essentially, so change in time. So this will give me average speed, right? And the meaning of average is more clear to us with the example of speed. So this will give me average speed. Now it is the ratio, average speed essentially is the ratio between the distance traveled and the time taken to cover that distance, okay. So that would essentially be the difference quotient, right? F of t plus delta t minus ft upon delta t. This is what is speed. This is what is speed. That's what is here. Now that's my average speed. You understand what is an average speed? Now what is instantaneous speed? The moment I try to look at the point where the time taken is almost zero, the change in time is almost zero, it's happening at that instant itself. What is the change in speed, at that instant itself? That is instantaneous speed, and that is calculated by looking at the change in time being almost zero. So the change in time being almost zero. As delta t goes to zero, delta t upon or delta d upon delta t is essentially ds by dt. S is some distance, okay, some distance. I didn't want to put it as dd, so I'm putting it as ds, okay. S is basically the distance function, so it is dt, okay, the function of time. Distance is the function of time, right? So that will give me instantaneous speed, okay. Now let me just give you an example of what we are actually talking about. So say my distance is 8t square. This is 8, okay. So my distance is 8t square. Find the average velocity between time t equals to 1 and t equals to 4. Now average speed or average velocity, I've told you, is nothing but del f upon del t, right? So that would be essentially, if s, I'm taking it as s distance, So change in S is what? S4 minus S1, and change in time is 4 minus 1. Okay. So S4 would be 8 into 16, 8t square minus 8 into 1 square, so 8. That would give me 40 meter per second, in case meter per second is the unit, in case time is in second and distance is in meters. Now, in the same question I ask you then, what will be the instantaneous velocity at time equals to 1? Okay. Then that would be ds by dt at 1. Okay, t equals to 1, which will be ds by dt will be 16t, because it's 8t square. We have learned how to find out the derivative of polynomial. So that would be 16t. So 16t is equal to st plus delta t minus st upon delta t, right? It will be equal to, we can just substitute 8t square as my function, so distance function, so 8t plus delta t whole square minus 8t square upon delta t. So just open it up, what you get, this will cancel out the remaining terms inside, and you can cancel out it with delta t as we have been doing, so it will be essentially 16t. Okay, so this was a direct derivative. This is by using the difference quotient. Okay, the difference quotient at time equals to 0 will give me 16 meters per second. Okay, so just see the difference between the average was 40 meters per second, instantaneous is 16 meter per second. So that's the difference between instantaneous and average. And that's a very good example of the usability of the interpretation of derivative. Interpreting derivative as in terms of usability. Now, a lot of time velocity, speed is used in maths and physics. Similarly, there are applications when we are looking at prices, cost in economics where we use it. So derivatives have a huge scope in terms of academics.